Hello everybody, today we will discuss a new topic, finite automata and regular languages. Specifically, deterministic finite automata called DEFA and regular languages. The finite automata are the simplest formal machines considered by computer science theory. They are an excellent tool to introduce some important concepts like state, transition, and indeterminism, among others. DFA are used to analyze source code in programming and extract the lexical items to compile them. Text editors use DFA to find words or patterns in text. They are also used in industrial control. Finite automata has the following characteristics. The system is always in a state, and the set of states is finite. They can replicate to a finite number of events. The state where the system is found can summarize all the information relative to past events. The reply to an event is determined only in function of the event and the state where the system is located. For example, a switch or an elevator. Finite automata that recognize languages. To us, the modeling work of a finite automata is to answer if a word belongs to a language or not. That's our point of interest. The most common way to imagine a finite automata is a machine with a central unit and a header able to read a tape, where it can find symbols from left to right. Those are the symbols to be read. Now in the picture you will see it very clear. It's very simple. This is an automata in the start point of most commonly called initial state. There is a strip of a tape with symbols and a header that reads them. There is a control unit that, according to the strip, change the state. It begins with Q0 when the header still has read any of the symbols. In the beginning, the control unit is in the initial state Q0, and the header is at the most left, still has not read any symbol. Hasn't read any symbol, and it reads from left to right. In every time unit, the header moves one position to the right, reading the symbol below. The control unit determines the new state from the current one and the symbol just read. The change of state is called transition. Here we have transition from Q0 to Q1. Here the header has read the first element, A, and then the control unit determines the change the state from Q0 to Q1. The machine states are divided into two categories: acceptor final states or not acceptor states. When the machine is located in a final state, that means the symbols string from the start to the end of the tape form a word that the machine recognizes as a word that belongs to the language L. If not, the word has not been recognized as belonging to L. It is said that the word has been rejected. When the header arrives to the end of the tape, Apple is the same. And here we have the most common representation, finite automata graphic representation. The states are cycles, like this. The initial state will have an arrow pointing at it, like this. This automata begins with A. Final states have two circles, may be found with a growth. Two circles. The transitions from a state to a state have an arrow from state to state or to itself. These are the transitions from the same state and from state to state. They will have the tag with the symbol that caused the change. This is the symbol A and B. So here we have the initial state A, the final state D. To say that the word has been accepted, the last state must be a final state at the end of the tape. So we have this automata. Let's try some words and we will see if they are accept or reject. When we start here, state A, so the first word begins with B. We go from A to C because the input is B, C. Then goes to A, remains the same, B and B. This is called a dead state or a trap state. A state where once inside, it's impossible to go out. So the word is reject because it's not in D at the end of the string. The second word begins with A. We begin as start A. From A we go to B. Then another B. From A we go to B and we arrive to the final state. But still one B remains in the final state, but an A. And we end the string in a non-acceptor state, so the word is also rejected, although we have passed by the final state, but at the end of the string we are not in a final state, so the word is rejected. And to finish the examples, word 3 begins with an A B, and then a B, and then an A, but a final B. So the word 3 is accept because it ends in a final state. Okay, and what does this automata? So let's study it. We start with A, but if the word begins with B, then it ends. It doesn't do anything more. The word is rejected automatically. So must begin with A. But then what happens is if it's A, it remains with B. So it must have a B, an A and a B. And what happens if it goes to A? It has an A, so it returns to a non-acceptor state. So to be in the final state must be a B. So what it does, this automata, is to accept all the words that begins with A, and doesn't matter if it's A or B in the middle, it must end with B. Finite Automata accepts words that begins with the symbol A and finish with the symbol B. It doesn't matter what's in the middle. Formally, what we will see most commonly, the language has words, and this word has a variable, an X, that belongs to the all alphabets, and the words must begin with A and end with B. It doesn't matter what's in the middle. That's all for this video. We see next video and we will discuss more finite automata. See you.